So this is cylinders problem number 3, and it's a closed cylindrical container is to have a volume of 300 pi cubic inches. So this information here is the constraint. And so we know for the constraint then that the volume is required to be 300 pi, and the volume of a cylinder is the radius, involves the radius and the height, and it is the area of the base, which is a circle, pi r squared times the height, and that is required to be 300 pi. The function we want to minimize is the cost. We want to minimize the cost, and the cost involves the fact that the top and the bottom cost $2 per square inch and the sides cost $6 per square inch. So we could kind of write that out in words and say, well, the cost is equal to $2 times the top plus the bottom plus $6 times the area of the lateral surface, or we'll say the side, meaning the band around here. That band around the sides of the rectangle, or the lateral area, of the cylinder, the lateral area of the cylinder is a rectangle. And so this little formula here is based off of the area of a rectangle. So we'll get to that in just a minute. So the cost, we'll just call it C, is equal to 2, meaning the $2, times the top, which is a circle, pi r squared, plus the bottom, which is a circle, another pi r squared, plus $6 times the lateral surface area, which the lateral surface is the circumference, 2 pi r, of this circle times the height. That formula, 2 pi r squared plus 2 pi r h, is given on your handout, but you should be familiar enough with it that you could figure it out on your own. So if we clean this up, we have C is equal to 2 times 2 pi r squared plus 12 pi r h, which is 4 pi r squared plus 12 pi r h. So we want to minimize the cost equation, but it has two variables right now, r and h. So we need to get cost as a function of just one variable, and it will be easier to get rid of the height than it would be the radius, because there are two radii in this. So we are going to take this equation and solve it for h, so that we can get the constraint into the equation, and then we'll also get rid of the h in this equation. So 300 pi divided by pi r squared, the pi's cancel, so h is equal to 300 over r squared. So the cost as a function of the radius of the can is equal to 4 pi r squared plus 12 pi r times 300 over r squared. So the cost as a function of the radius simplifies to 4 pi r squared. 300 times 12 is 3600 pi over just r, because this r and the r squared cancel. Alright, so this is the function that we want to minimize, and we want to graph it here. So we have radius, r for radius of the can, and then going up here is cost. Now the problem with this, if we just try and graph it, is we have no idea what the costs are for this, and so we need to guess a couple values to see ballpark about how high the costs can get for various radii of this cylinder. So if we know that the volume, pi times the radius squared times the height, has to equal about 300 pi, then we've got to figure out some numbers here such that when you multiply r squared times h, you get about 300. So those numbers can't end up being very big, because maybe if r was 10, 10 squared is 100, then h would be 3. That would be fine. If r was 20, though, then r squared would be 400, and h would have to be smaller than 1. So I know that r is probably not 20. It could be 10. It could be, say, 5. 5 squared is 25, and then 5 goes into 300 12 times. 25 goes into 300 12 times. So that would be reasonable. So anyway, that gives you some idea. You need 3 numbers that multiply to 300, and that gives you some idea of what your r should be. So I'm going to guess, let's say 10. If it's at all within range, 10 is a good number because it just makes the math kind of nice and easy. So if r is 10, then h, which is equal to 300 over r squared, 10 squared is 100, so 300 over 100 is 3, and then this is cost, because that's what we're trying to minimize, and that's what's on the y-axis here. That's the function that we worked hard to get. Will be either 4 pi r squared plus 3600 pi over r, or 4 pi r squared plus 12 pi r h. You can use either one of these formulas. This one just has r in it, and this one has r and h, but they're equivalent. They'll give you the same answer. So I'm going to use a calculator to get that. And so I'll try this one here. 4 pi times the radius, which is 10, squared, 4 pi r squared, plus 12 pi times the radius times the height. So the typical cost, if the radius was 10, the cost is up to 2,387. Alright, and in this case, since the radius is 10 and the height is a lot smaller, I'm going to try guessing something smaller for the radius. Maybe 6. And if the radius is 6, then 300 divided by 6 squared would be 300 divided by 36. This is to find the h value, is 8.3. And then I'm going to do the same formula I just did. And I can press second enter to bring back this, and then I can put in 6 instead of 10, and 6, and then 8.3. Now technically I should use 8.3 repeating, but this is just an estimate to get the size of the window, so it doesn't have to be exact. So, oh, again, about 2300. Alright, so 2329. All right, so I'm looking for a minimum cost, and I know that I have some costs in the 2000s. So I'm going to double that, roughly, and say that this is 5,000. And then 10 and 6 are my radii, so I'm going to double those and say about 20. I could be wrong, I might need to adjust that, but that's what I'm going to try. So now I'm going to get the calculator back and go to y equals and type in the function 4 pi times the radius squared plus 3600 pi divided by the radius. And then the window, we're hoping this is right, 0 to about 20, and scale by 2s, and 0 to 5,000, and I'll scale by 1,000. Alright, give it a try. So that looks great. So I'm going to sketch that in here in just a minute, and while I'm on this screen we could second calculate value and make sure that we've got this going right. You can check your guess. When x is 10, y is 2,387. So I know that things are working correctly. And then remember that every point on this graph gives you a cylinder with a volume of 300 pi. So when x is 10 and h is 3, the volume is 300 pi and the cost is 2,387, which is pretty cheap comparatively to this. It's almost near the bottom, but it's not the least amount of cost. So every point on here has the volume of 300 pi, but we want the one with the least cost. So the least cost is the minimum. So we do second calculate minimum, move to the left, press enter, move to the right, press enter, move about to the minimum, press enter, and so we know that the correct answer is 7.663. So I'm going to draw this in here about like this, and I know that this minimum is 7.663, and the cost was 2,213.805. So 2,213.805. Alright, so I can't quite fit that decimal value in there, but that's close enough. So then the answer to the question, remember that these values are radius, comma, cost. And the question is, find the dimensions of the container of least cost and what is the cost. So the radius is 7.663 and the height is 300 divided by that. 300 over the radius squared. Doesn't look like a 3. And so I'm going to do that here. And this 7.663 is stored in the variable x. So if I quit out of here and do 300 divided by x squared, then it will use that 7.663 number for me. You can tell that that's right because if you just press X and enter, you can see the 7.66. So when I did 300 divided by x squared, the x variable was using 7.66, which is my radius. So this is 5.109. And the least cost is 2,213.51. We'll round to the nearest penny since it's money. And let me check that answer. Yep, 2,200. My answer here says 81. Was that right? Second calc, minimum, move to the left, move to the right, enter. Oh, yep, 81. So 2,213 and 81 cents. All right, there you go. So the only difference if you were doing this problem using calculus is instead of using the graphing calculator to find the minimum, you would be able to do something to the function, an algebraic operation to the function called taking the derivative, and you would be able to find this minimum point without using the graphing calculator. So it's a good pre-calculus problem just to practice getting this function, because that's the hardest part. Actually doing the calculus to get from here to the answer is the easier part in calculus. So that's why we're practicing these problems so much.